Hello students, welcome back. I don't want to complete section 3, but I do want to complete example 3.3. So let's go back here. We completed up to part B. So x squared plus 1 is congruent to 0 mod p has a solution if and only if p is a prime of p is an odd prime of the form 4k plus 1, or equivalently speaking, x squared is congruent to -1, or in other words, -1 is a quadratic residue of p if and only if p is an odd prime of 4k plus 1 form. We went through that. Now let's answer the next question, and we're going to have to use this. Prove that there are infinite many primes of the form 4k plus 1. Before starting this, do you remember this problem? The infinite many primes of the form 4k plus 3. We did it in lesson 4. And then we're going to come back and complete this. By the way, how about 4k plus 2? No, there's only one. P is 2 and nothing more. That's the only even prime. And 4k plus 0, nothing, because the remainder is 0. That means divisible by 4. So it's not a prime. So we can classify odd primes in 4k plus 1 form and 4k plus 3 form, and we know there are infinite many of this form. Now we are going to prove infinite many of this form as well. Here's a symbolic expression. It's a prime, and then it's just 4k plus 1 form. Alright, suppose that there are finite many such primes, p1, p2, p3 of the pn. Just like the way we proved there are infinite many primes to begin with. Way back in lesson 3, or was it lesson 4? I think it was lesson 4. In lesson 4, we did something like this. And then P1, P2, P3, like this. And then we went from there, remember? And then this thing is congruent to 1 modulo all pk's. So not divisible by any prime. We went through that argument here, but this time things are a little bit different. We want square here and then 2 squared, so 4 times something plus 1 form. Okay, alright, that's the starting point. Now let's make an observation. N is odd. Yeah, this is even. 2 is there, so this is even, and plus 1, so n is odd. So there is an odd prime p that divides n. In other words, this capital N is congruent to 0 modulo p, where this p is an odd prime. So flip this one to the other side. This thing squared is congruent to -1 mod p. So what did you get? And in terms of Legendre symbol, we can say -1 over p is 1, positive 1. Or in terms of quadratic residue, we can say -1 is a quadratic residue of this p. So it should be of 4k plus 1 type. So this p is one of those pi's. You see? Suppose that there are finite many such primes. Such prime, we want to prove the primes of this form, 4k plus 1 type. Those are finite many, and named all those. And then we ended up with -1 is quadratic residue, so it's a 4k plus 1 type. So this p is actually one of those pi's. So p is one of those pi's, those listed. But then again, that's impossible, because if p is one of those pi's, then this thing is congruent to 0 modulo p. So capital N is congruent to 1 mod p. You see, this thing here is 0, so n is congruent to 1 mod p. But then again, previously we said n is congruent to 0 mod p. It can't be right. It's a contradiction. Where did you get this contradiction? Where did you make an assumption? Well, suppose that there are finite many such primes. That's got to be false. So there should be infinite many of those. So we got that. The infinite many of odd primes of this form, 4k plus 1. By the way, we have some time left, so let's have a review on what we did in lesson 4. The infinite many primes of the form 4k plus 3. Remember that? How did you do that in lesson 4? Well, suppose that they are finitely many. So P1 through PR, so multiply them all and 4 and then plus 3. Obviously, I'm trying to get 4k plus 3 form. And then Q is divisible by any primes of form 4n plus 3 because, you see, this is congruent to 0 and we have plus 3. So this capital Q is not divisible by any primes of 4n plus 3. Now it is not divisible by any primes of the form 4n plus 1 type either because let's see, if capital Q can be factored by all the primes of 4n plus 1 form, well, previously I used k and now I'm using n, so it can be a bit confusing. Sorry about that, but it's a second problem, different problem. So prime factorization of capital Q, 4n1 plus 1, 4n2 plus 1 up to bunch of them, and then they're all congruent to 1 modulo 4 because, you know, this one has 4, those have 4. But then again, if you go back to the original, 4 times something, so capital Q is congruent to 3 mod 4. In this viewpoint, congruent to 1 mod 4. In this viewpoint, it's congruent to 3 mod 4. So there goes a contradiction. So that's the way we did in lesson 4. In any case, this kind of assumption, suppose that there are finitely many, and multiply them all and some expression and plus something, that trick is common here. A little bit different, of course, but multiply them all, some expression and plus something. And then, of course, there are infinite many primes, Euclid's theorem. Again, multiply them all and then read it plus 1. So that's a common technique being used. That's a nice thing to remember, I guess. Anyway, this way we completed exercise 3.3, example 3.3. And alright, that's where we're going to conclude lesson 13. In lesson 14, we'll actually review those and then restart from section 3. You may want to skip if you want to.